Hello, everyone. Today, I will talk about sampling constraint satisfaction solutions in the local lemma region. This is joint work with Weiming and Yitong. Constraint satisfaction problem is one of the most well-studied subjects in computer science. Let V be a set of variables where each V takes its values in domain QV. Let C be a set of constraints defined on these variables, where each constraint C is defined on a set of variables VBL-C. It maps the assignments of these variables VBL-C to satisfied or unsatisfied. A solution to the set P is an assignment of variables such that all constraints are satisfied. Some important examples of CSPs include CNF formula and hypergraph coloring. Given a CF instance phi, which consists of a set of clauses defined on Boolean variables, a solution of phi is an assignment of all Boolean variables such that phi is true. Given a hypergraph H and a color set Q, a solution of hypergraph coloring is a coloring of all the vertices from Q such that no hyper-H is monochromatic. A fundamental criterion for the existence of constraint satisfaction solutions is given by the Lovász local lemma. Given a CSP instance phi, let each variable v independently take values from QV uniformly at random. Then, each constraint C can be regarded as a body event BC, where BC happens if and only if C is violated. Let P be the maximal probability of the body events. Moreover, the dependency relationship between these events can be characterized with a dependency graph, where each vertex is corresponding to a body event, and any two body events, BC1 and BC2, are adjacent if and only if C1 and C2 share variables. Let D be the degree of the dependency graph. The symmetric Lovász local lemma is as follows. If EP times D plus 1 is no more than 1, then the probability that none of the body events happens is larger than 0. Equivalently, the CSP instance has a solution. Now, we apply the Lovász local lemma to CNF and hypergraph coloring. Consider the case CNF where the number of variables in each constraint is k. Let D denote the max number of constraints a variable appears in. By the Lovász local lemma, we have if k is greater than or equal to log D, then the CF instance has a solution. Here we ignore the high-order terms. Similarly, for hypergraph coloring, by Lovász local lemma, we have if Q is larger than C times delta to 1 over K minus 1, then the instance has a solution. Here, C is a constant, Q is the number of colors, and the delta is the maximal H degree. The original Lovász local lemma only provides the existence of a constraint satisfaction solution. In recent years, plenty works have been devoted to the algorithmic triple L, which finds a CSP solution efficiently. A major breakthrough was the Moser-Tallis algorithm, which finds a solution in linear expected resampling steps if the local lemma condition holds. In this paper, we are concerned with a problem that we call the sampling triple L, which sample a CSP solution uniform at random efficiently in the local lemma region. This is a distribution-sensitive variant of the algorithmic triple error and has got a lot of attention. The problem is closely related to the approximate counting, which estimates the total number of solutions. Besides, it may also serve as a standard toolkit for solving the inference problems that are well motivated from machine learning applications. Previously, some progress in sampling triple error has been achieved on specific applications. For hypergraph coloring, Magnus, Martin, and Marek proposed an algorithm which is fast in the region that Q is larger than delta and K is no less than 4. Then Alan and Paul proposed a new algorithm. The algorithm achieves an improved region, but is only applicable to linear hypergraph. These regions are far from the triple L region. In 2018, Hen et al. Improved the region greatly. However, the running time of the algorithm is n2 poly delta k, which is too slow if delta OK is large. For KCF, Hen, Mark, and Jingchen proposed an interesting sampling algorithm. The algorithm achieves the region k is greater than or equal to 2 log d, but has an extra condition on the intersection lower bound between the clauses. In a breakthrough work, Moitra improves the bound to k is greater than or equal to 60 times log d. However, the running time is n2 poly delta k. Recently, Weimin et al. Proposed a much faster random algorithm. The resulting sampling algorithm enjoys a close to linear running time with an improved region k is greater than or equal to 20 times log d. Remark that their technique uses special properties of CNF. There is some barrier in the application to hypergraph coloring. In this paper, we further improve previous bounds. For hypergraph coloring, we propose an algorithm which samples a uniform coloring approximately if k is larger than 28 and q is larger than 50 times delta to 9 over t minus 12. Its running time is square of q times cube of k times square of delta times n to 1 plus 1 over q. The condition matches the local lemma region q is larger than delta to omega 1 over k. And the running time is a fixed polynomial in n, q, k, and delta. For KCF, our algorithm samples a uniform solution approximately if k is larger than 13 log d. Its running time is square of d times cube of k times n to 1 plus eta, where eta is a small constant. This result improves previous bound k is larger than 20 log d. Our algorithm is also applicable to all atomic CSPs. Given a CSP, if a constraint is violated by exactly one assignment of its variables, this constraint is called atomic. A CSP is atomic if all the constraints are atomic. Recall that each CSP instance can be formulated as an instance of the Lovász local lemma. Let P be the maximal probability that a constraint is violated and D be the degree of the dependency graph. By the Lovász local lemma, we have if log in 1 over P is larger than log in D, then the atomic CSP has a solution. In this paper, we propose an algorithm which samples a uniform solution of atomic CSP approximately if log in 1 over P is larger than 350 times log in D. The running time of our algorithm is square of D times K plus Q times n to 1 plus eta. Here, Q is the maximum size of the domain, K is the maximum width of the constraint, and eta is a small constant. Our algorithm can also be extended to general CSP. For a general CSP instance, if each constraint forbids at most n configurations, then each general constraint can be decomposed into at most n atomic constraints. Then we have the following corollary. If log in 1 over p is larger than 350 times log in d plus log in n, then our algorithm samples a uniform solution of general CSP approximately. A powerful method for sampling the solutions of CSP is the Markov chain. Global dynamics is a kind of natural Markov chain. Given an instance of CSP with uniform distribution mu of solutions, global dynamics starts from an arbitrary CSP solution X. For each transition step, it picks a variable v uniformly at random, and resamples the assignment of v, xv, according to the conditional distribution of mu, conditional on the assignment of other vertices. It can be proved that if the solution space is well connected, then the global dynamics is rapid mixing. If the solution space is connected but there are many breaths, then the global dynamics is slow mixing. If the solution space is not connected, then the global dynamics is not mixing. For CNF and hypergraph coloring, it has been proved that the solution space is not connected. Thus, new algorithms are proposed for these problems. There are mainly two different approaches. The first approach is sampling one deterministic counting. The approach first constructs M, Xm, where M is a subset of V and Xman M is an assignment of the vertices in M. Here, M and Xm should satisfy the pre-Gibbs property, such that, given Xm, one can recover the target distribution mu by sampling the assignment of the vertices in V set minus M according to the conditional distribution mu V set minus M conditioned on Xm. Usually, Xm is constructed on linear programming, and Xv set minus M can be contrasted by brute force algorithm. The total running time of this approach is n to poly decay. Another approach is sampling one projected MCMC. In this approach, the algorithm first constructs a set of marked variables M, then samples Xm from mu_m with MCMC, where mu_m is the marginal distribution of M in the target distribution mu. Then, the assignments of the vertices in V set minus M can be obtained by rejection sampling. Though the approach is fast, the good mark set may not exist for general CSP. In this paper, we propose a new technique called the state compression. Our goal is to bypass the connected barrier of global dynamics. The original solution space of CSP is not connected. This technique compresses faraway states into one state, such that the projected space is well connected. To show how to realize the state compression, we need the following notations. Let pi be the uniform distribution over all possible assignments. Then, The target distribution mu is the conditional distribution of pi, conditioned on that all the constraints are satisfied. A projection scheme is a set of functions hv, where hv is a mapping from qv to some sigma v, where the size of sigma v is no more than qv. The projected distribution of mu is nu. If x follows the distribution mu, then the projection of x as x follows the distribution nu. The algorithm for sampling from mu is as follows. The algorithm first constructs a good projection scheme H. Then it samples x from pi and let y be hx. Then it runs a global dynamics for nu. At each transition step, it picks a vertex v from the set big V uniformly at random, and then resample yv according to the conditional distribution. At last, it samples x from the conditional distribution of mu, conditional on that hx is equal to y. To make the algorithm efficiently, the following conditions are necessary. Firstly, the good projection scheme exists and can be constructed efficiently. Secondly, the global dynamics on projected distribution is rapid mixing. Thirdly, sampling from the conditional distributions is efficiently, including sampling yv given y v set minus v, and sampling x given hx is equal to y. In our algorithm, the sampling from conditional distribution is through inverse sampling. Given a projected configuration sigma on the subset lambda of V and a subset S of V, the inverse sampling of sigma on S outputs a random sample XS, the marginal distribution of X on S, such that X is sampled from mu, conditional on the projection of X on lambda is equal to sigma. Thus, to sampling an x from mu, conditional on hx is equal to y, it is to perform the inverse sampling inverse yv. To performing the global update of yv, it is to perform the inverse sampling inverse y v set minus v v, and let yv be the projection of xv. Thus, the algorithm can be rewritten with the inverse sampling. To make the algorithm efficient, it is required that the inverse sampling can be implemented efficiently. Thus, the projection scheme should be carefully designed. On the one hand, the projection should substantially compress space to get a well-connected projected space, such that the global dynamics is fast mixing. On the other hand, the projection cannot compress the original space too much, such that the inverse sampling is efficient. Formally, the projection scheme should satisfy the entropy criterion. For each vertex V, the number of assignments QV is partitioned to SV buckets. The first item is to make sure that the size of the buckets are almost the same. In the second item, the first inequality is to make sure that the projected space is much smaller than the original space, such that the projected scheme substantially compresses the original space to a well-connected projected space. The second inequality is to make sure that the projected space is large enough such that the original space is not compressed too much. These inequalities can be rewritten as follows. Here, Hxv is the entropy of Xv. This term is the entropy of Yv. Intuitively, the projection scheme should compress the entropy by a certain proportion. For example, our projection scheme for hypergraph coloring is as follows. The original domain is Qv, the set of Q colors. The projected domain is sigma v, the set of S buckets. The number of buckets is around Q to 0.227, and the number of colors in each bucket is around Q to 0.722. Our sampling algorithm for hypergraph coloring is as follows. Firstly, we decompose each hyperedge E to Q atomic constraints, such that each constraint forbids a configuration where all the vertices are with the same color. Then, we run our algorithm for atomic CSPs. The key is how to implement the inverse sampling. Consider a constraint C that forbids all red coloring. Let Y be a projected configuration on sigma. If there is a vertex V in lambda such that the red color is not contained in the bucket YV, then the constraint C must be satisfied conditional on Y. In this way, we can check whether a constraint is satisfied. By removing the satisfied constraints, the original CSP will be decomposed into disjoint sub-CSPs. With high probability, these sub-CSPs are with polylog size. Thus, we can perform the inverse sampling as follows. The algorithm first decomposes the original CSP to sub-CSPs according to Y lambda, where each sub-CSP is very small. Then performs rejection sampling at each sub-CSP. Thus, the final assignment X can be obtained by combining Y lambda with the assignments of the sub-CSPs. At last, the assignment of X on S is returned. In summary, we proposed a new algorithm for sampling Lovász local lemma. This algorithm improves the bounds of hypergraph coloring and K-F, and it runs in polynomial time for all atomic CSPs. Our main technique is state compression, which substantially compresses the original space to get a well-connected projected space. There are some open problems. The first one is to design a fast algorithm for general CSP. The running time of our algorithm depends on n, where n is the maximum number of configurations that a constraint forbids. Recently, Jen, Fan, and Wang proposed an algorithm for general CSP with running time n to polydecay. Is there an algorithm for general CSP with running time polynomial in d, k, and n? In this paper, our algorithm works for K-F if k is no less than 13 log d. Recently, this bound is improved to k is no less than 5.741 times log d by Jane, Fan, and Wang. On the other hand, it is proved that if k is no more than 2 log d, then sampling a solution of K-F is intractable. So, what is the tight bound of K-F? Similarly, our algorithm works for hypergraph coloring if Q is no less than 15 times delta to 9 over k minus 12. Recently, this bound is improved to Q is no less than delta to 3 over k minus 4. So, what is the tight bound of hypergraph coloring?